The Gimli Glider is the nickname of an Air Canada aircraft that was involved in an unusual aviation incident. On July 23, 1983, Air Canada Flight 143, a Boeing 767-233 jet, ran out of fuel at an altitude of 12,500 meters above MSL, about halfway through its Montreal to Edmonton flight. The flight crew was able to glide the aircraft safely to an emergency landing at an auto racing track that was previously RCAF Station Gimli, a Royal Canadian Air Force base in Gimli, Manitoba. The subsequent investigation revealed a combination of company failures and a chain of human errors that defeated built-in safeguards. The amount of fuel that had been loaded was miscalculated because of a confusion as to the calculation of the weight of fuel using the metric system, which had recently replaced the imperial system for use with the 767. History. On July 22, 1983, Air Canada's Boeing 767 flew from Toronto to Edmonton where it underwent routine checks. The next day, it was flown to Montreal. Following a crew change, it departed Montreal as Flight 143 for the return trip to Edmonton, with Captain Robert Pearson, 48, and First Officer Maurice Quintal at the controls. Captain Pearson was a highly experienced pilot, having accumulated more than 15,000 flight hours. First Officer Quintal was also very experienced, having logged over 7,000 hours of total flight time. Running out of fuel on July 23, 1983, Flight 143 was cruising at 12,500 meters over Red Lake, Ontario. The aircraft's cockpit warning system sounded, indicating a fuel pressure problem on the aircraft's left side. Assuming a fuel pump had failed, the pilots turned it off, since gravity should feed fuel to the aircraft's two engines. The aircraft's fuel gauges were inoperative because of an electronic fault which was indicated on the instrument panel and airplane logs. During the flight, the management computer indicated that there was still sufficient fuel for the flight, but only because the initial fuel load had been incorrectly entered because the fuel had been calculated in pounds instead of kilograms by the ground crew, and the erroneous calculation had been approved by the flight crew. Effectively, this error meant that less than half the amount of intended fuel had been loaded. Because the incorrect fuel weight data had been entered into the system, it was providing incorrect readings. A few moments later, a second fuel pressure alarm sounded for the right engine, prompting the pilots to divert to Winnipeg. Within seconds, the left engine failed and they began preparing for a single-engine landing. As they communicated their intentions to controllers in Winnipeg and tried to restart the left engine, the cockpit warning system sounded again with the "all engines out" sound, a long bong that no one in the cockpit could recall having heard before, and that was not covered in flight simulator training. Flying with all engines out was something that was never expected to occur and had therefore never been covered in training. Seconds later, with the right side engine also stopped, the 767 lost all power, and most of the instrument panels in the cockpit went blank. The 767 was one of the first airliners to include an electronic flight instrument system, which operated on the electricity generated by the aircraft's jet engines. With both engines stopped, the system went dead, leaving only a few basic battery-powered emergency flight instruments. While these provided sufficient information with which to land the aircraft, a vertical speed indicator that would indicate the rate at which the aircraft was descending and therefore how long it could glide unpowered, was not among them. On airliners the size of the 767, the engines also supply power for the hydraulic systems without which the aircraft cannot be controlled. Such aircraft are therefore required to accommodate this kind of power failure. With the 767, this is usually achieved through the automated deployment of a ram air turbine, a hydraulic pump driven by a small turbine. which is driven by a propeller that rotates because of the forward motion of the aircraft in the manner of a windmill, as the Gimli pilots were to experience on their landing approach. A decrease in this forward speed means a decrease in the power available to control the aircraft. Landing at Gimli in line with their planned diversion to Winnipeg, the pilots were already descending through 35,000 feet where the second engine shut down. They immediately searched their emergency checklist for the section on flying the aircraft with both engines out, only to find that no such section existed. Captain Pearson was an experienced glider pilot, so he was familiar with flying techniques almost never used in commercial flight. To have the maximum range and therefore the largest choice of possible landing sites, he needed to fly the 767 at the optimal glide speed. Making his best guess as to this speed for the 767, he flew the aircraft at 220 knots. First Officer Maurice Quintal began to calculate whether they could reach Winnipeg. He used the altitude from one of the mechanical backup instruments, while the distance traveled was supplied by the air traffic controllers in Winnipeg. Measuring the distance the aircraft's echo moved on their radar screens, the aircraft lost 5,000 feet in 10 nautical miles, giving a glide ratio of approximately 12:1. At this point, Quintal proposed landing at the former RCAF station Gimli, a closed Air Force base where he had once served as a Royal Canadian Air Force pilot. Unknown to him or to the air traffic controller, a part of the facility had been converted to a racetrack complex, now known as Gimli Motorsports Park. It includes a road race course, a go-kart track, and a drag strip. A Canadian Automobile Sport Club's sanctioned sports car race hosted by the Winnipeg Sports Car Club was underway the Saturday of the incident. The area around the decommissioned runway was full of cars and campus. Part of the decommissioned runway was being used to stage the race. Without power, the pilots used a gravity drop which causes gravity to lower the landing gear and hopefully lock it into place. The main gear locked into position, but the nose wheel did not. This later turned out to be advantageous. As the aircraft slowed on approach to landing, the ram air turbine generated less power, rendering the aircraft increasingly difficult to control. As the runway drew near, it became apparent that the aircraft was coming in too high and fast, raising the danger of running off the runway before it could be stopped. The lack of hydraulic pressure prevented flap-slat extension, which would have, under normal landing conditions, reduced the stall speed of the aircraft and increased the lift coefficient of the wings to allow the aircraft to be slowed for a safe landing. The pilots briefly considered a 360-degree turn to reduce speed and altitude, but decided that they did not have enough altitude for the maneuver. Pearson decided to execute a forward slip to increase drag and lose altitude. This maneuver is commonly used with gliders and light aircraft to descend more quickly without increasing forward speed. As soon as the wheels touched down on the runway, Pearson braked hard, blowing out two of the aircraft's tires. The unlocked nose wheel collapsed and was forced back into its well, causing the aircraft's nose to slam into, bounce off, and then scrape along the ground. This additional friction helped to slow the airplane and avoid injuring the people on the ground. After the aircraft had touched down, the nose began to scrape along the guardrail in the center of the tarmac. Pearson applied extra right brake, which caused the main landing gear to straddle the guardrail, creating additional drag which further reduced the speed. Air Canada Flight 143 came to a final stop on the ground 17 minutes after running out of fuel. None of the 61 passengers was seriously hurt. A minor fire in the nose area was extinguished by racers and course workers armed with fire extinguishers. As the aircraft's nose had collapsed onto the ground, its tail was elevated and there were some minor injuries when passengers exited the aircraft via the rear slides, which were not long enough to accommodate the increased height. Investigation. The Aviation Safety Board of Canada reported that Air Canada management was responsible for corporate and equipment deficiencies. The report praised the flight and cabin crews for their professionalism and skill. It noted that Air Canada neglected to assign, clearly and specifically, the responsibility for calculating the fuel load in an abnormal situation. It further found that the airline had failed to reallocate the task of checking fuel load. The safety board also said that Air Canada needed to keep more spare parts, including replacements for the defective fuel quantity indicator, in its maintenance inventory, as well as provide better, more thorough training on the metric system to its pilots and fueling personnel. The final report of the investigation was published in April 1985. Fuel quantity indicator system. The amount of fuel in the tanks of a Boeing 767 is computed by the fuel quantity indicator system and displayed in the cockpit. The FQIS on the aircraft was a dual-processor channel, each independently calculating the fuel load and cross-checking with the other. In the event of one failing, the other could still operate alone. But under these unusual circumstances, the indicated quantity was required to be cross-checked against a float stick measurement before departure. In the event of both channels failing, there would be no fuel display in the cockpit, and the aircraft would be considered non-serviceable and not authorized to fly. Because inconsistencies had been found with the FQIS in other 767s, Boeing had issued a service bulletin for the routine checking of this system. An engineer in Edmonton duly did so when the aircraft arrived from Toronto following a trouble-free flight the day before the incident. While conducting this check, the FQIS failed and the cockpit fuel gauges went blank. The engineer had encountered the same problem earlier in the month when this same aircraft had arrived from Toronto with an FQIS fault. He found that disabling the second channel by pulling the circuit breaker in the cockpit restored the fuel gauges to working order, albeit with only the single FQIS channel operative. In the absence of any spares, he simply repeated this temporary fix by pulling and tagging the circuit breaker. A record of all actions and findings was made in the maintenance log, including the entry, service CHK, found fuel QTYI ended blank, fuel QTY number 2C, be pulled and tagged. On the day of the incident, the aircraft flew from Edmonton to Montreal. Before departure, the engineer informed the pilot of the problem and confirmed that the tanks would have to be verified with a float stick. In a misunderstanding, the pilot believed that the aircraft had been flown with the fault from Toronto the previous afternoon. That flight proceeded uneventfully with fuel gauges operating correctly on the single channel. On arrival at Montreal, there was a crew change for the return flight back to Edmonton. The outgoing pilot informed Captain Pearson and First Officer Quintal of the problem with the FQIS and passed along his mistaken belief that the aircraft had flown the previous day with this problem. In a further misunderstanding, Captain Pearson believed that he was also being told that the FQIS had been completely unserviceable since then. While the aircraft was being prepared for its return to Edmonton, a maintenance worker decided to investigate the problem with the faulty FQIS. To test the system, he re-enabled the second channel, at which point the fuel gauges in the cockpit went blank. He was called away to perform a float stick measurement of fuel remaining in the tanks. Distracted, he failed to disable the second channel, leaving the circuit breaker tagged. The FQIS was now completely unserviceable, and the fuel gauges were blank. On entering the cockpit, Captain Pearson saw what he was expecting to see: blank fuel gauges and a tagged circuit breaker. Pearson consulted the minimum equipment list, which indicated that the aircraft was not legal to fly with blank fuel gauges, but due to a misunderstanding, Pearson believed that it was safe to fly if the amount of fuel was confirmed with measuring sticks. The 767 was still a very new aircraft, having flown its maiden flight in September 1981. CGAUN was the 47th Boeing 767 off the production line, and had been delivered to Air Canada less than 4 months previously. In that time period there had been 55 changes to the MEL, and some pages were blank pending development of procedures. Because of this unreliability, it had become practice for flights to be authorized by maintenance personnel. To add to his own misconceptions about the condition the aircraft had been flying in since the previous day, reinforced by what he saw in the cockpit, Pearson now had a signed-off maintenance log that it had become custom to prefer over the MEL. Refueling at the time of the incident, Canada was converting to the metric system. As part of this process, the new 767s being acquired by Air Canada were the first to be calibrated for metric units instead of imperial units. All other aircraft were still operating with imperial units. For the trip to Edmonton, the pilot calculated a fuel requirement of 22,300 kilograms. A float stick check indicated that there were 7,682 liters already in the tanks. To calculate how much more fuel had to be added, the crew needed to convert the quantity in the tanks to a mass. Subtract that figure from 22,300 kilograms and convert the result back into a volume. In previous times, this task would have been completed by a flight engineer, but the 767 was the first of a new generation of airliners that flew with only a pilot and co-pilot. The volume of jet fuel varies with temperature. In this case, the mass of a liter of fuel was 0.803 kilograms, so the correct calculation was 7,682 L times 0.803 kilograms. L equals 6,169 kilograms. Fuel already on board 20,088 L times 0.803 kilograms. L equals 16,131 kilograms. Fuel to be transferred to plane 27,770 L times 0.803 kilograms. L equals 22,300 kilograms. Fuel for flight. The ground crew had arrived at an incorrect conversion factor of 1.77, which was the weight of a liter of fuel in pounds, and this error was not noticed by the flight crew. The conversion factor provided on the refueler's paperwork was one that had always been used in the past, when Air Canada's fleet had been imperial calibrated. Their incorrect calculation was 7,682 L times 1.77 pounds. L equals 13,597 pounds. Fuel already on board 4,916 L times 1.77 pounds. L equals 8,703 pounds. Fuel to be transferred to plane 12,598 L times 1.77 pounds. L equals 22,300 pounds. Fuel for flight. Instead of 22,300 kilograms of fuel, they had 22,300 pounds on board, 10,100 kilograms. About half the amount required to reach their destination. Knowing the problems with the FQIS, Captain Pearson double-checked their calculations but was given the same incorrect conversion factor and inevitably came up with the same erroneous figures. The flight management computer measures fuel consumption, allowing the crew to keep track of fuel burned as the flight progresses. It is normally updated automatically by the FQIS, but in the absence of this facility it can be updated manually. Believing he had 22,300 kilograms of fuel on board, this is the figure the captain entered. Because the FMC would reset during the stopover in Ottawa, the captain had the fuel tanks measured again with the float stick while there. In converting the quantity to kilograms, the same incorrect conversion factor was used, leading him to believe he now had 20,400 kilograms of fuel. In reality, he had less than half that amount. Aftermath. Following Air Canada's internal investigation, Captain Pearson was demoted for 6 months. and First Officer Quintal was suspended for 2 weeks for allowing the incident to happen. 3 maintenance workers were also suspended. In 1985, the pilots were awarded the first-ever Fédération Aéronautique Internationale diploma for outstanding airmanship. Several attempts by other crews who were given the same circumstances in a simulator at Vancouver resulted in crashes. Quintal was promoted to captain in 1989. Pearson remained with Air Canada for 10 years and then moved to flying for Asiana Airlines. He retired in 1995. The aircraft was temporarily repaired at Gimli and flew out 2 days later to be fully repaired at a maintenance base in Winnipeg. Following the successful appeal against their suspensions, Pearson and Quintal were assigned as crew members aboard another Air Canada flight. As they boarded the aircraft, they realized that airplane was the same one involved in the Gimli incident. After almost 25 years of service, the aircraft flew its last revenue flight on January 1, 2008. Air Canada still uses the flight number 143, but the route is now Montreal, Ottawa, Edmonton, or St. John's, Halifax, Ottawa, Edmonton using an Embraer 190 aircraft. However, this was not the only incident involving this flight number of Air Canada as of June 26, 2015, where an E-190 at St. John's with this same flight number was targeted in an alleged bomb threat.